Hi, I'm Joshua Lee, and in today's video, we're going to be learning about Newton's 3 laws of motion, which were published in 1687. You've probably heard of Sir Isaac Newton, and maybe you have heard of the legend where an apple fell on his head. Newton's 3 laws are fundamental to understanding the motion of objects and how they behave, and they're also very important when learning about kinematics. So let's cover the first law. This law talks about the inertia of objects, which is why it is sometimes referred to as Newton's law of inertia. You may be wondering what inertia is. Well, simply put, inertia is an object's tendency to keep doing what it was doing. This law is also stated as an object in motion will remain in motion and an object at rest will remain at rest unless acted on by a force. So this means that in order to change an object's velocity, you need enough force. Let me give you an example. Let's say you have a beach ball and a bowling ball, which both have the same volume. However, the bowling ball is obviously going to have much more mass. The bowling ball, therefore, is going to be harder to move and harder to stop once it is moving. This means that the bowling ball has more inertia. Inertia is directly related to mass, and objects with more mass tend to have more inertia. So to sum up, objects always try to keep their state of motion unless acted on by some other force. Let's move on to the second law. This law states that the net force is equal to mass times acceleration. This law is pretty straightforward and can be put into the equation F net is equal to ma. It's important to know here that this is the net force, which is the force that is left over after adding up all the other forces, since they might cancel out. When all the forces acting on an object are balanced out, this state is called equilibrium. An object doesn't have to be staying still to be at equilibrium. It could still be moving, but it won't be experiencing any acceleration. This shows that acceleration is caused by an imbalance of forces acting on an object. Newton's second law is useful for calculating the weight of objects. Let's look at another example. Let's say that you throw up a 5-kilogram ball straight up into the air, and then it starts to fall back down due to gravity. Well, let's calculate the net force then. The net force, or F net, would be equal to mass times acceleration. We know that the mass is 5 kilograms, and we know the acceleration of gravity is 9.81 meters per second squared. So if we multiply these two numbers, we get that the F net is equal to 49.05 kilogram meters per second squared. We often use these types of equations a lot, so we sometimes write the equation as Fg equals mg, where g is the acceleration of gravity and Fg is the force of gravity acting on the object. The force of gravity acting on an object is also known as its weight. Now remember the unit I mentioned earlier, kilogram meters per second squared? Well, we can just simplify that into a Newton. So weight is measured in newtons after Isaac Newton. Despite common belief, weight isn't measured in kilograms. Kilograms is a measure of mass. Now for the last law. This law is important because oftentimes there is more than just one force acting on an object. You probably know this law as, for every action there is an equal and opposite reaction. This means that if you exert some amount of force on an object, the object will exert an equal force back on you. A good example would be normal force. Normal force is the force exerted on an object by another stable object or a surface. Normal force is generally perpendicular to the surface that the object is resting on. So, if I put a box on top of a table, the normal force will be acting upwards, since that's the direction that's going to be perpendicular to this surface. There's also gravity pulling this box down, so the forces are balanced and it won't be accelerating. However, if the object is on a slope, so like this, then the normal force won't be pointing straight upwards. It'll be pointing in this direction, since that's perpendicular to the surface. So, Newton's third law says that if a force is applied to an object, the object also exerts an equal force back. Let's say that you and one of your friends are on a surface that is perfectly frictionless. The closest would be probably standing on ice. If you pushed your friend act this way, what would happen? Well, you might think that you will stay in your original position while your friend moves forward, since you applied the force to them. But according to Newton's third law, your friend applies an equal force back on you, so you would also move backwards. But now you may be wondering how things can move if everything applies an equal force back. For example, what if I was trying to drag a box? How would I move the box if it applied an equal force back on me as I was trying to drag it? The answer is that things can move because there are often more forces than just the action-reaction forces, which all differ in magnitude. Here is me pulling a box attached to a rope. Every time I take a step, I push the ground back, and the ground pushes me forward. At the same time, I pull the box forward while the box pushes me backwards. However, the force from the ground pushing me forward is stronger than the force from the box pulling me back. So, this force is stronger than this force, so I am able to pull the box forward. Now let's learn about free body diagrams. A free body diagram is a model that shows all the forces acting on an object. So let's do a free body diagram of an object resting on a table just as an example. So this will be our table and this is the box. First, we put a dot in the middle of the object, like this. Then we use arrows to show the forces. Gravity pulls down on the object, so it is represented by an arrow pointing down, like this. But there's also normal force, which is exerted on the box by the table, so it points up. So it counteracts gravity, and all the forces are balanced. Since all the forces are balanced, we know that the box is not accelerating. This means that the net force acting on the box is 0. What if that same box was suspended from a rope from the ceiling? Well then, gravity is still acting on the box, but now the counteracting force is a force known as tension force. Tension force is force that comes from ropes, strings, and wires. When we use tension force, most of the time, we assume that the rope has no mass and is completely unbreakable. So the tension force can change depending on the box's weight. Now let's draw the free body diagram. Again, we draw the dot in the middle. Again, gravity is still acting on the box, so it points down. Now the counteracting force isn't normal force since it isn't resting on a surface, but rather tension force, which comes from the rope. Since we assume that the rope is completely unbreakable, the interesting about tension force is that its value can depend on the weight of the object. So if this weight here was 5 newtons, this tension force would also be 5 newtons. If this weight was 10 newtons, the tension force would also be 10 newtons. So, tension force can vary in value. Let's look at a harder problem. Here's a diagram of a pulley system. There's a large rock here and a smaller rock here, connected to each other by a rope. This rock has a mass of 1,000 kilograms. The smaller rock has a mass of 850 kilograms. Since this rock is heavier, it'll go down, which will make this rock go up. Now, what is the acceleration of the rock falling down? Let's start by looking at the force of gravity for both of these rocks. The force of gravity, Fg, acting on this big rock will be its mass times the acceleration of gravity. So we know the mass is 1,000 and gravity is 9.81. So the force of gravity will be 9,810 newtons. So this force will be acting downwards since it's falling down. At the same time, there is tension force pulling this large rock up. So the net force for this rock, so F net, will be equal to F tens, which is the tension force, minus the Fg, or mass times g, mass 1. Now let's look at the smaller rock. Let's calculate the force of gravity again. So Fg will be equal to 850 times 9.81. So this turns out to be 8,338.5 newtons. And again, the F net, the net force, is equal to the F10s, the tension force, minus the mass times gravity, or the Fg. So mass 2 times g. Thanks to Newton's first law, we know that the F net is equal to ma. So we can substitute ma for both of these F nets. So we get two equations. The first will be negative ma m1a is equal to F10s minus m1g. Now this ma is negative since the rock will be falling down, so the acceleration will be negative. Now for the second equation, we get that ma m2a is equal to F10s minus m2g. If you're wondering why these masses, m1 and m2, have numbers, well, they're there to make sure that we don't get confused whether we're talking about the mass of the first rock or the second rock. So here, this m1 refers to the mass of the first rock, the bigger one, or this m2 refers to the smaller rock. Now, we don't know the F10s and the acceleration. Now, by the way, the acceleration will be the same for both of these rocks, since this rock falls and this rock goes up. Well, we don't need to know the F10s, so we can cancel them out using systems of linear equations. So we can subtract this first equation from this equation, the second equation, and when we do that, we get the equation m1g minus m2g is equal to m1a plus m2a. Since we're looking for acceleration, we can rearrange the equation using algebra to get that a is equal to g times m1 minus m2 divided by m1 plus m2. Now, if we substitute all the values that we know, we get that a is equal to 9.81 times 1,000 minus 850 over 1,000 plus 850. Now, if we calculate all of this, the final acceleration will be about 0.795 meters per second squared. Now, this is just the magnitude of the acceleration. Since the big rock is going down, the real acceleration would be negative 0.795 meters per second squared. In today's video, we learned about Newton's 3 laws, free body diagrams, and solved a question relating to these concepts. I hope you enjoyed this video. Please subscribe, and thanks for watching.